My name is Michael Hansen, and in this video I would like to show you some practical examples on how to use Lenstool, or perhaps you could say a program like Lenstool, because this is what I'm about to show you here is sort of general in all cases for most of the software out there for modeling gravitational lensing. So first of all, I'd like to introduce to you the windows I have opened on my screen. Over here you can see a terminal where I'm going to type in commands. You'll see that. Here I have a text editor. At this point here you can see a list of different sources. These markers here means that these sources here has been commented out and will be ignored by Lenstool. And here you can see the model parameter file, which I will also introduce later on. So let's get started. So the first thing to notice in this model.par file, this is the primary parameter file for Lenstool. Now this particular parameter file has been set up in a slightly different way, because in this parameter file I am actually not modeling or optimizing images optimizing a given set of parameters, giving some images, but here I'm actually doing the reversed. I am giving Lenstool some fixed parameters, and then I'm going to output some images. I chose to do this in order to show you, sort of in a quite reasonable way, how images will change when you change the position of the source. So let me introduce the parameters for you. Here you can see there's profile and a 1. 1 means that it is the singular isothermal ellipse. If I, for example, wrote 81, it would be the dPIE profile. So, but here I'm going to use the singular isothermal ellipse. The x-center and the y-center is in arcsecant with respect to this reference point up here. I've chosen 64 dot for the rectus sensation and -24 for the declination. You can actually use what you want. If you're modeling an actual cluster out there, then ideally you would choose real coordinate systems, which means that you will replace this with actual coordinates you would derive from the images that you have from the Hubble Space Telescope, or where you have them. Now, since this is the singular isothermal ellipse, maybe I could write that here, SIE. You can see that I also have an ellipticity, which I have set to 0 here, and I have an angle position, which I have also set to 0. Because, as you hopefully know, if I have an ellipse, I can always reduce the ellipse to a circle by setting the ellipticity to 0 or 1, depending on which system you're using. And the angle position becomes irrelevant when we have a circle, because if you rotate a circle around its center, then no matter what angle you rotate it in, it will retain the same shape. We also have the velocity dispersion, which I have set to an arbitrary number here, which could be somewhat typical for galaxies, 422.932 kilometers per second, and the redshift I have also chosen arbitrarily, 0.396. Some of you might remember that this is the exact same redshift that I've used in my master thesis. Then down here we have the grill, or grid, as it is called. Nombre means how large the grid can be. For Lenstool, the standard maximum is 128. Polar means whether to use polar coordinates or not. We don't use polar coordinates here. And n lentil is the number of lenses. since I have only one SIE profile, this number is 1. This source parameter here is sort of irrelevant because I have the Redshift in the source catalog. Observe, binning, I only bin 1, so I get the full resolution. You could set it to 2 or 3 or whatever you want. Seeing, I have set the seeing to 0.5. That is sort of excellent seeing on Earth. These two parameters is not relevant here. They sort of just defines whether they should put in some noise in the picture and how this noise should be distributed. And the sky determines how much background noise you would expect from the sky. Cosmology, model 1, just means that we're using the standard cosmological model. H0 is the Hubble constant, 70 kilometers per megaparsec per second squared, I think it is. Omega matter, 0.3. Omega lambda or omega x, 0.7, the standard values. Omega k is the curvature, it's 0, there's no curvature. And these are specifically defined in relation to the distribution of the dark energy. Then we have the C-line parameter down here, where we can set some planes. I have chosen to retain any, but as you can see here, if I put if I put in a 4 here, I would get critical lines and caustics for redshift, this redshift, this redshift, this redshift, and this redshift. This is how large the grid should be in arcseconds. So please remember that this parameter part here means that it would be 150 times 150 times 2, because it is 150 on one side, 150 on one side, and 150 and 150. So it would be 300 times 300. The algorithm, marching squares is the usual. Limit high and limit low defines how much resolution you want on your critical lines and caustics. If you choose too low resolution here, then you would get holes in your critical lines and caustics. Grande, well, grand. I actually, to be honest, really don't know what this parameter part here is really about. Lenstool needs it, but it is just the standard values. Champ, some of you who know a little bit French might know that this means field. So this means that my field for most of the outputs I get is 20 arcseconds. It means it is 40 times 40 arcseconds. Alright, let's go to the top. You already know the reference parameter. Source, it's my source list, as you can see here. Mass means that I output a mass image. Pixel is where I get the images. And verbose, it just means that we get some extra information. If I set it to 0, you'll just get the absolute necessary information to see that Lenstool is running. Alright, I'll just save it, and then we can look on the source part here. These 4 A sources here is the sources I want to show you what happens when we move the source from the center and out. The S sources here is some sources I already defined, but I'll show you how it looked for optimization of a singular isothermal ellipse or sphere. Alright, so let's start. Let's run Lenstool with this parameter file here. So we just write Lenstool model -n, sorry. Then we can see that Lenstool runs, and then we can try to open this file, the image file that we got, to make an images. So here you can actually see an Einstein ring. Like I said, the lens would be somewhere in here. We can, for example, open a new frame, and then we can open the m.fits. Here you see the lens, and if we blink those, you can see that, hopefully see that the distance is almost the same from the lens and out. Alright. Let's just go back to frame 2. So this is when the source, as you can see here, I've shown you the source is positioned at 0, 0, 0, 0. This refers to the ellipticity of the source that I'm using. This is the position angle, this is the redshift, and this is the magnitude. So this is not this is the flux. This isn't used in Lenstool, but it is there. Alright, so let's try to do some other things. Let's try to choose another source like this. We still have no, let's just wait a second. Let's use this again. No, we'll do what we do this. Alright, sorry. And let's run the code again. And you can see here that it performs a fast Fourier transform and creating a seeing filter and all sorts of things. It's related to this. You can see if I set the scale to set scale, you can see some noise here. This is the sky background that we get. So it tries to emulate if we actually had a real image from a CCD, that we would get some noise both from the sky background and from the CCD itself. But I'll just set it to this value here. Alright. So let's see what happened when I moved the source a little bit. 0.5 to 0.5. Oh, now we got two images. You can possibly see, I'll try to change the scale a bit. You can perhaps see that they are a little elongated. Even though this is truly a singular isothermal sphere, you can see that they are a little elongated, but we don't have a ring anymore. We have two images, one here and one here. And if we blink again, you can see that one image is fairly closer, a little bit closer to the lens than the other. So I would surmise that the source would be somewhere around here, which possibly is okay. Alright, so let's go back to the images. Let's try to run it with where we have moved the source a little bit more. I'll run Lenstool again, and we'll get, see the images has moved. They moved some distance in this direction here, but the distance between them is still the same. But you can possibly see that this image here is a little less magnified, and this image here is also a little, this is demagnified, and this is actually a little less magnified. If I blink again, you can see that the source would be possibly somewhere around here. And you can see that this image gets closer to the lens and this image gets further away. Let's just take this and set it to single. Alright, so let's move the source again. This time out to 2.0 and 2.0. And let's run Lenstool. It found two images, as you can already see here. Let's take a look. Images.fits. You can see that this image here gets a little less magnified. This gets demagnified, but this gets also a little less magnified. And if we blink again, you can see that this image is very close to the source. Now, if we had the lens here, remember that this is just the images. If we had the lens, you can probably imagine that we wouldn't see this image here because it would be obscured by the light from the lens. Please do remember that these images that I'm showing you here, the image of the mass here, is a mass estimate from this run here, so it doesn't have any physically to do with an actual galaxy, but it's more to show you how the images and the source would be positioned with respect to the lens. So let's try to put another source in here. because I must admit I was actually expecting this to be one image alone. Let's put it at 4 and see what happens. Now we get one image. So let's take a look. One image here. And that is because the source have moved past the Einstein ring. You saw the Einstein radius, you saw the ring before. So the source would be probably somewhere around here. Let's blink it. The source would be somewhere around here, I think. Alright. So let's try another thing. Let's try to make the Einstein ring again. But this time we'll make it an ellipse instead of a sphere. And we'll run again, see what happens. Now you can see it says it has found 4 images. If we get a perfect Einstein ring, it would probably say something like 50 images or maybe more. But let's take a look. See, now we got something else. We actually got 4 images. Because even though we have an Einstein, we have an single isothermal, even though we have the source at the exact center of the lens, we no longer have a sphere. We have an ellipse. And if you can see, let's try to decrease the ellipticity, and we would get something more like an Einstein ring. You can see we still get 4 images. Let's try to see how it looks. See, now we get more like an Einstein ring. Let's further decrease the ellipticity. Now we get 9 images, as you can see here. And now we almost practically got an Einstein ring. You can possibly see that it's a little more thick around here than it is. Let's try to make it like something like this. Now you can see here, one of the nice things about Lenstool is that you can experiment like this. Now we still got an, see, we have an image here, an image here, an image here, and an image here. Now, to be fair and honest, like this, there are essentially virtually no completely spherical galaxies in the universe. They are almost always elliptical in shape, but they can be very spherical, almost to the point where you would say that they are actually spherical. Now, as you probably can imagine, I've cheated a little bit because I've also given the source a little ellipticity. Just a little, but it is there. Alright, so now I'm going to show you an actual optimization. And I'm going to use these parameters. I'm going to cut them, so we have them always. Put them in a new document. Let's remove this here. No, let's leave it be. Let's put it out here. Let's make it as small as possible, so that we can always remember these numbers. Because I'm going to close this part here, and I'm going to open another window. But first I'd like to show you what we're going to optimize for. So you can see we find 2 images here. Now remember, like I said, the singular isothermal sphere and also the singular isothermal ellipse doesn't provide us with the third central image somewhere in here. It just doesn't, because it is singular. Now if we choose a dPIE profile which is not singular, or any other profile that is not singular, we will get the third image in here. Alright, so let's take a look at the images now. So these are the images that we're going to optimize for. Now, what you would do in sort of actual sense, and know what images are what here. You can probably sort of imagine that these images belong to each other, these images belong to each other, and these images belong to each other. You can try to blink. So you can possibly also imagine that for some of the images the source would be here, for some of them it would be here, and for others it would be somewhere around here perhaps. Yeah. Let's put it to, single. There. But like I said, what you would do in actual, when you got, first of all, when you got images of an actual galaxy with actual multiple images, you wouldn't have images like this. First of all, you'll probably have a much better resolution, especially if you use the Hubble Space Telescope. But you would also have images. You would take your observations, your images from your observations in different filters, so all of these images here would have different colors so you could distinguish them. But what you would do then, you can use a program to find your images, the position of your images, find the centroid. But if you wanted to, you could also let's reduce the scale a little bit so we can get a better understanding of where the centroids are. So you can see here we would probably say that we have a centroid somewhere around here, 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 and somewhere around here. Something like that. Then you would take your regions here. Take your regions. This is one way to do it, and change it to get it in coordinates like this. Then you would copy these coordinates here and put them in a catalog, which I'm about to show you now. Let's take a look. So here we have the optimization catalog. I'm going to close these files here. Then I'm going to open the model and the image file. So you can see here, let's just delete these regions, yeah, and then delete this frame, and delete this frame, make a new frame, and then we're going to open another image that I have here. Here you have the images that I just shown you. Yeah, let's sorry. Here, something like this. Yeah, that's okay. Here you have the galaxy in the middle. This is the lens, and these are the multiple images that you can see. Now, if this works, you will get to see where the images actually are. It didn't, unfortunately. So we're going to do something like this. Then we're going to open the file. It was called Galaxy 1. Yeah. This sometimes happens like this. You can see it again. Then we're going to adjust the scale a little bit so we can better see what's on the image. Yeah, this is good. Then we're going to run the same command again. And now you can see the images. So 1, 1 and 1, 2 is here. 2, 1 and 2, 2 is here. And 3, 1 and 3, 2 is here. This is what you see here. This is the position. Reference 0 means that these are in absolute world coordinate systems. You could also take them as distance from a reference point in world coordinates. Then you would say 3 here instead, and then something like 64 minus 24, I think it is that I chose. Something like that. You can see it here. Yeah, minus 24. But since it would screw up the calculations if I did it like this, I'm just going to keep it the right way. So let's look at how it looks when we're going to optimize. So the reference, still the same. Then we have a mass part here, still the same. I have removed the source part here, so I haven't got any sources, of course, because I'm giving Lenstool images. Then I have an inverse part here. It is how Lenstool would like to invert the equation. As you can see here, 3 means that we're going to use the Bayesian optimization. 0.05 is the burn-in parameter. If I set this to 1, I would get a relatively fast burn-in phase. You can try that. Try to run it. Lenstool model. Let's let it run. You can see that the burn-in phase went relatively fast, but I might exclude some important parameter parts. Let's stop it and set it to 9 like this. Just check that let's try to run it again. So you can see that the burn-in phase goes relatively fast. And then we're going through the sampling phase, where we're going to sample all the different model parameter parts in order to find the best model. Now if I just stop Lenstool and set the burn-in parameter to, let's set it to 0.01. Let's try to set it to 0.001 and see how long the burn-in phase takes. You can see it explores much more of the parameter space. You can see it here by the burn-in exploration here. It takes a lot longer time to get to any true reasonable value, as you can see. This is usually not necessary. A burn-in parameter value of 0.05 is usually enough to get a good burn-in phase. And let's set it to 2000 instead. Let's go on. The restart parameter file here, or the restart option here, is not relevant. If I uncomment it, Lenstool will create a restart file, so if my computer goes down or the server is restarted or something like that, then I can just restart my calculation. It's actually very nice, because when you have a lot of multiple images and if you have for example, a very big cluster with a lot of multiple images and a lot of cluster members, then the burn-in phase, particularly in the image plane optimization, can be very slow. Take many days. Now here you see in the other part I call this grill. Grill. I could also call it grid, which is more English, I guess. Number, still the same. Polar, still the same. Polar, yeah, it's the same parameter. Lentil, still the same. I have 1. Lens crit means that I'm going to calculate the critical lines and the caustics for one lens, because I have one lens. And in lens opt means how many I want to be optimized. Still 1. This is going to change in the other part I'm going to show you. Here we have the image file. So I tell Lenstool that I have a mult file. You can see here 1 means that there's a file, and this is the name. Mult WCS is not, this is deprecated, sorry. But I have it here anyway. Form is how I want to optimize. So if I write 0, let's do that. I'm going to optimize in the source plane optimization. Let's try that, see how fast it goes. Very fast, as you can see. But essentially, like I said, it is imprecise. Essentially it's wrong, but a better word would be to say that it is imprecise. This is typically done, like I said in the previous video, to sort of narrow in your parameter space. Because I only have one potential here and a reasonable limited parameter space, there's no need to use the source plane optimization. Set M limit, this part here, parameter value here, is set to 0, 1 and 1. This should be 0 also. This is basically means that if you have images in your image list, like you have it here, where you may have, these are all emulated to be spectroscopically confirmed images. That is, we are reasonably sure that this is the actual redshift of these images. If you have photometric redshift, then these are usually very insecure, and instead you can optimize for the redshift of the images. So what you would write is, for example, 1 here, because you're going to optimize. This would be the name of the image. So for images 1112, you would write 1, like I've done. For images 2122 and so on, you would use 2 and 3. You can also write specific images if you have that, or a list of images here. But usually you write families of images. This 1 here that you usually write means that these values here are strict, and this is ignored when we're using the Bayesian optimization. Sig PostArcsec is the position error of the images in arcseconds. If you have an Hubble Space Telescope image which with a resolution of 0.06 arcseconds, you would usually use that for starters, but eventually you would crank up the position error. Also, in order to avoid including parts of structure along the line of sight and such things in your analysis. I'm going to show you how you can actually specify what signal position, position error you should have. So here's the mean, the meat of the parameter value, the parameter file. This is the potential for G1. I could also call it, let's just call it galaxy. This is the parameters for this galaxy here. Now remember, these images here are from a mock catalog that I have created myself. That is also why I know where the center of the images should be, of the potential, what the ellipticity should be, the angle position, the velocity dispersion, and the redshift. Now, the redshift is the same. It has to be. So let's just write it here, 396. Also check that I have done the same up here in the mass. Yes, 396. That's very important. Again, these are the initial values that I give it. I have been told that Lenstool ignores this when you optimize. I'm not sure about this, but you should put them in anyway, because they sort of give you an idea of where your potential is with respect to the parameter values. Profile is 1 because I'm using a singular isothermal ellipse. I have initially set the ellipticity and the angle position to 0 because I'm emulating a circle. Now remember, this is what we can test here. I have actually set an ellipticity and an angle position when I created these images, but we can try to first see how well a singular isothermal sphere will constrain the parameters, these actual parameter values, and then we can try to optimize for the ellipticity. Here is the limit part. I've called it cluster 1 because I copied it. Let's call it gal also. I have three parameters here. When we're dealing with a galaxy lensing, you usually lock these parameter values down because you're pretty sure that when you have galaxy lensing, you only have galaxy lensing. So you can be pretty sure that the center of your galaxy is actually also the center of your mass. But if you want to be absolutely sure, you can also optimize for the center in y and x and y. Now, as you can see here, I have set x and y center to 0.0. There's also another option. I could set it to WCS. Then I would have to use, let me just change this. Then I would have to put in the center of the lens using these values. You can see at the, I can't point with the mouse because then it would go away, but you can see here that if you look up in the top of DS9, you can see there's FK5. Then you can see there's an alpha and a delta. And these are the world coordinate system coordinates of this galaxy. So I would put that in there instead. I don't want to do that because it is not necessary. So when it's written like this, it means that this is the distance from the reference point in arc seconds. And this is the same here. I'm going to explore from... Now this is very important when you do this. -10 and 10 means that it's going from -10 to 10. So it is -10 with respect to the reference point to 10 with respect to the reference point. So if I, for example, imagine that I had another galaxy here, I couldn't just use -10 and 10 instead, because this would be a completely different position with respect to the reference point. So I had to use that. Alright, and I'm also only optimizing now for the velocity dispersion, as with the singular thermal sphere, which I just opened up. So I'm going from 10 to 700 because I don't have many images and I don't have many free parameters, so it won't take that long to optimize, even though it's going to take a little while. So let's try to run it as it is. I'm going to save it. Let's try to see what happens. Remember that I'm optimizing in image plane mode now, so it will take a little longer time. So what happens here is that as the burn-in phase here, the burn-in values here approaches 1, we say that the burn-in has converged. And then we start when the burn-in phase has converged, which it has now, then we start the sampling instead. Now for some reason my computer doesn't like, this is a little laptop, doesn't like to be run as hard as it is here now. I might get a little better result by letting it use another processor. I'm going to do that. Let's use 2. Now you might ask yourself, why don't I just use all 4 processors on my computer? I have, this is a Core i5, so I have 2 processors and 2 additional threads from hyperthreading. But the thing is that when you are dealing with a relatively low number of constraints and a relatively low number of free parameters, especially the constraints, by letting the computer use or your server use a lot of processors, you would actually use more processing time on switching the calculations between all the different processors than you would do in the actual optimization. Since I don't expect it is very interesting for you to see these numbers slowly climb up, I'm going to pause the video and then return when it is done. See you in a bit. Alright, so now you can see the run has finished, you can see the chi-square, you can see the evidence, and you can see that it has calculated critical lines and caustics for these redshifts here. And you can also see that we have a mass fits file. Now you can do a lot of things with these outputs here. I'm going to show you the results from a few of them. So let's first look at the chi-square. It's 38. Let's open the best.par. So you can see here that we have 3 free parameters. We have 3 degrees of freedom, and we have a chi-square of 38, and we, as you saw before, we have a position error of 0.3. Now I'm going to show you a way how to deal with this, because the ideal case is to have the number of degrees of freedom should be the same as your chi-square number. So you can probably imagine if I set this to be lower, like 0.01, I would get a higher chi-square. Alright, so let's try to calculate this. I'm going to use IPython to calculate it. No, sorry. I'm sorry. I'm going to use Pylab extension, like this, Pylab extension. Alright, so the idea is to take, when it starts up, the square root of the redshift, sorry, not the redshift, the chi-square, 38.4364, divided by the number, the degrees of freedom, that's 3, and then multiply that by 0.30. Then we get 1.07. Let's put that in. Yes. And let's run Lenstool again. While Lenstool is running, I'm going to show you something else. You might have noticed that I used a command called PELI. This is a standard command that comes with Lenstool, so if you have Lenstool installed on your system, then you also have the PELI. With this you can take any file that you might have containing coordinate points or position points for images that you have, the potentials that you have calculated, the position of the cluster members if you have some of them, anything you can imagine that Lenstool can read. You can output this directly to DS9 as I have here, and you probably noticed that I used a command where I wrote PELI and then the image WCS file, then I wrote red because I want a red color. I wrote 0, 0. It refers to whether PELI should automatically clear any image, any any region files that you might have. Essentially it's the same as saying delete all regions. And then I used point last because I want a point like this. If I don't use point, I get a circle with the same radius as you see it here, so it would be a radius of 1 arcseconds. No ellipse, so it would just be a circle. But here you can see, and this, if you have a lot of images that you have put in, for example, from an article, and you want to be sure that you are actually having the correct position of these images, and you have a lot of images, then using the pally command and then checking all these images is a very good idea. Alright, so this is one way to ensure that you are actually giving Lenstool the right images. I'm going to pause the video again and then we'll return when the optimization is almost finished. See you later. So now that Lenstool is almost finished, let's take a look and see what the results might be. Alright, it's finished, so let's take a look at the best.par file. This gives us the best parameter values. So we have 3 degrees of freedom still. We have a chi-square of 3. So in this essence we have 1. When we divide the degrees of freedom with our chi-square, we get 1, which is what we wanted. So let's initially take a look at the parameter values. So we got minus 0.27 as the center, 0.21, it's fairly close. We got 403 as the velocity dispersion, but the reason why I did this is to get correct errors. So let's try to use another tool that is also included with Lenstool called bias results.pl. It's a Perl script. So what this tool will do is to read the bias.dat file. You can see that we have 6 columns here, 20,000 lines, because there are 2,000 different models. Remember that Lenstool for some reason adds 1. So if I had written 2000 here, I would get 2010 lines, 2001 model, but I want 2000 just to, because that's the way I am. You can see here the errors. So we have the position X, the best value is 0.2732. That's what we got here, right? Yes, 32. But the error is, if you look at the Gaussian error, it is plus minus 0.3, so somewhere around 0 actually. But you can also look at this error here, it is somewhere between almost plus 1 minus 1. So the best parameter value that we get is definitely within 0.0, which is what we gave the model. And the same goes for the Y, 0.2134. The errors is plus 9, almost plus 1, and minus 1.21. So again, within 0.0. Now remember, we are not actually modeling the system in a strictly correct way, because I have used an ellipse. This is a singular isothermal ellipse that I'm trying to emulate or sort of estimate by using a singular isothermal sphere. So in essence you can sort of check how well the singular isothermal sphere will do for a clearly elliptical system. Let's look at the velocity dispersion. For the best value we got 403.3, or just 403, and we got plus minus 38, sorry, we got plus 38 minus 37. So definitely the correct value is within our error bars. You might also notice that the median is closer, both the median and the mode is closer. So the median, you hopefully know, it is the median. The mode is the most prevalent number, so this is the number that is found in our bias.dat file the most times. So let me just open the bias.dat so you can see it. Is that? So you can see we have the number of samples, we have the likelihood, we have the position of x and y for 1 and the velocity dispersion, and then we have the chi-square. And you can see that we have 10 lines here with 1, 10 lines here with 2, 10 lines with 3, and so on, because there are 10 chains for each of the models here. Now all of these lines here, all of them represent one particular model that Lenstool has created. And remember, tested, sorry. And remember, the Lenstool tested, in this case, 20,000. It's 2,000 different models. So there's a lot of them. And then this tool here, bias.dat, uses all of these numbers here to calculate these values here. So what is that for? Well, as you might look at the best.par file here, and well, if you are working on a system that you don't know what true values are, you wouldn't do what I'm suggesting here. But in this case here, where I actually know what the correct values I used to create these images with are, I could look at these numbers here and say, oh, well, it's 422, 403, that's not close really. And even this is off, it should be much less. But when I look at the error bars here, which I calculate from the bias.dat, particularly asymmetrical errors here at, sorry, this is the wrong number, but it's at 99.7% confidence interval, or 3 sigma confidence interval, I actually see that my numbers are to some extent fairly reasonable within the error bars, even when I'm trying to approximate an elliptical galaxy with a spherical mass model, mass distribution. But let's try to run it as it is. So I'm going to add 2 new free parameters in here. I'm going to add the ellipticity, which I'm going to say, well, I'm going to 0.01 to 0.99. So I'm going to explore all the possible ellipticities. I wonder, to some extent, a good. Now this is not the precision on the parameter value or the parameter space exploration, but it's how many precision numbers I want on my output. All right. And let's take the other is the angle position. So I'm going to write angle pos. I'm going from 0 to 0 to 180.0. I just wonder, I don't need the precision to be that high on the angle position. I'm going to reduce the signal position, the error, to 0. Let's just put it at 0.5. It will make the optimization a little bit faster. And let's run Lenstool again. Remember, now I'm actually recognizing that I might have an elliptical system, so I'm using the singular isothermal ellipse as it is. Now you can see that I have 5 free parameters and I have 6 constraints. Now you might now imagine, what if I only had 2 multiple images and wanted to use this singular isothermal ellipse? Well, you're correct in assuming that I might have a problem with that. But as I said before, when we have galaxy-galaxy lensing, we are almost always sure, we can almost always assume, if not always, that the mass center of this galaxy is at the center of the emission of light. So in that sense, I can remove 2 free parameters, but I still have 3. So what could you also do? Well, you might try to do spectroscopy on your galaxy and then figure out what the velocity dispersion might be. And when you know the velocity dispersion, you could remove that as a free parameter. You could also remove that as a free parameter. And then you have, from 2 images, you would have 2 constraints, and you would have 2 free parameters, so that would work. But you are correct in assuming that given only 2 images, 2 multiple images, and a galaxy, and wanting to emulate this or optimize this as an ellipse, you would have a problem. Particularly because in real galaxy situation, you almost always have some kind of external shear. So in essence, you have the galaxy creating these images that you see, but you usually also have galaxies around this galaxy or something else perturbing the field here a bit, so they will move the galaxies a bit around. So you would almost always have to include some kind of external shear when you are optimizing galaxy-galaxy lensing, and that would include at least 2 new parameters for this external shear. So yes, you need enough multiple images in order to optimize such a system successfully. I'm going to pause the video again and then return when the optimization is done. Alright, while Lenstool is still running, I had to shift back and forth between the position error in order to get closer to 1, and now I'm down to 0.03, so let's see what it gets there. But before I'm going to show you that, I want to discuss with you or show you something else. Now, as you might have seen, I have 6 number of constraints, and some of you might have also seen that I have 6 images, so you might be led to believe that when I have 6 images I have 6 constraints, but that is not the case. The number of constraints that you have in a given system goes as the sum of 2 times n minus 1, where n is the number of images in a particular system. So in this case, I actually have 2 times 2 minus 1 plus 2 times 2 minus 1 plus 2 times 2 minus 1. That gives me 6. But I'm going to show you in a bit, just a bit, that when you have more systems with more multiple images, you don't only have the number of constraints that are equal to the number of images that you have. So let's take a look if it's finished. It is. So now I have an error of 0.12. Now I don't think I'll get it any better than that. Let's look at the best.par file. Yeah, I think that's reasonable. Now it should be closer to 1, but it's okay. It's hard to get it to 1 because, well, yeah, it is. So let's look at the numbers. Now we can take a look here, and now we can see that it is actually quite reasonable. So we have the x center is minus 0.02. That is almost 0. The y center is 0.07, almost 0. The ellipticity is 0.4. The true position is 0.303. The angle position is 126. The true position is 123. the velocity dispersion is 123. The true velocity dispersion is 422. So let's look at the errors on our system. So we get an error of the x in plus 0.045 in both cases. For the y we get plus 0.9 and 0.9. I'm looking at these asymmetric errors out here. For the ellipticity we got 0.4, and the error bars we get plus 0.03 and minus 0.02, so that is fairly close to the true number. The angle position we get 126.1, if you will. We got plus 2.1 and minus 2.5. That is also means that our angle position is reasonably close to the true angle position. And of course the velocity dispersion is as close as it can be, 423, and we got minus 2 and plus 2. So within the error bars we actually got a quite good representation using this system here. Now of course, as you know, you can probably see here that I set it down to 10,000 lines instead of I set it down to 1,000 different models instead of 2,000 different models. That might be the reason why we are close, but we could probably get closer by using 2,000 instead. But nevertheless, given the way that we are optimizing these things, remember that we are choosing the most probable model from a very large set of different models. Our parameter values actually got pretty close, and all of them within the error bars fits the actual values. Alright, I'm going to close these, and next I'm going to show you what we can do with a more complex system. So let's just change the values that we have and change this here. So here you see the mass distribution from, again, I created a mock catalog. And this time we have a bright cluster galaxy here in here, together with the center of a cluster, almost spherical cluster profile. It has a small ellipticity, and then we have some cluster members placed almost, you can see that they are placed symmetrically, but I've just put them there. And then I have also put in some sources at a vast number of different redshifts. So I'm going to show you the list of images that is reflect the list of sources. So let's take a look at yeah, sorry, not there. Let's see. Here it is. Let's open the model also. Yes. So you can see here we have a vast number of images. Let's take a look at the images. You can see them here. You can see the arcs. You can see that when we're dealing with a cluster, we get a much more complicated system. Now, of course, I've added more sources, but nevertheless, we also have many more images. We actually have 28 different images from 8 different sources. So now we can take a look at the idea we had before about the calculation. So let's see what we got. 2 times 3 minus 1 plus 2 times 3 minus 1 that is I'm going to 4 here, that is plus 2 times 3 minus 1 plus 2 times 3 minus 1 plus, now we have the 6, that is also 2 times 3 minus 1. This might go wrong because it's a lot more complicated. So here we have 5, 2 times 5 minus 1 plus 2 times 3 minus 1, that is the 5 here, and the 8s also have 5 images, so that is plus 2 times 5 minus 1. It should give somewhere around 40 constraints. Now you can see that we have 28 different images, but we get 40 constraints. So that is partly because we have some of the systems we have up to 5 images instead of the usual 2 images in the system before, and you can see a lot of them have 3 images. Now you might remember the idea with critical lines and caustics. So for the images, the sources that gives 3 images, we can conclude that the source is within the outer caustic for this particular redshift, and the images that the sources that gives 5 images are within the inner caustic for that particular redshift. You can also see that we have a much more variety, much larger variety on the redshift. We goes from 1.15 to 5.4. Alright, so let's look at the model parameters. Now, as you can see here, I've included parameter values for a dPIE profile for our cluster halo. As you can see here, I've set the core radius to 90, the cut radius to 10,000, should be a large number. The ellipticity is 0.3, so it's not that much elliptical. It's a little offset compared with the cluster galaxy. That's also in that catalog. It's called GALS, funny enough. So we can see a 10 is the reference galaxy. It is positioned. You might not be able to extract that from here, but you can see our reference point is 64 and minus 20, and here you have 63.999649, that is almost 64, and there you have minus 20.000247, that is almost minus 20. So this is in the smack center. Our cluster halo is a little offset, not much, but it's a little offset. You can also see that the velocity dispersion is 1250. For all the cluster members, the core radius has been set to 0.15 kiloparsecs. The magnitude is from the brightest, it is 17. The sigma, the velocity dispersion, has been set to 375. The cut radius has been set to 60. And the slopes has been fixed to 4 and 2.8571, as is consistent with constant mass to light ratio. Sorry, I should have said that as media slope. Yeah. All right. No, I shouldn't say that. Let's see. Yeah, that is okay. All right. So let's try to run this. You can see we have 40. Let's try to. We have calculated that we have 40 constraints. Let's calculate the number of free parameters. So we have 1, 2, 3, 4, 6 here, and we have 2 here. So that's 8 free parameters and 40 constraints. So we are reasonable within the limits of being able to constrain this system. All right. So well, let's run it. Before I run it, I should tell you that on my laptop I'm going to run it in the source plane optimization mode. I use a position error of 0.5. I have set fairly open parameter priors, as you can see here, -10 to 10 in the position, 0.01 to 0.99 in the ellipticity, and so on. The idea is that I first run this particular model here in source plane, and then I use that to constrain or restrain my priors to run it in image plane, because given that I've added many more multiple images and also more systems, remember that even though I have only 8 free parameters, I have something of 11 galaxies within the system, so I actually have 12 different profiles in an actual sense, even though the 11 of them is optimized via the scaling relations and not individually like this. But let's run it and see what happens. So you can see even in source plane optimization, even using the many more free parameters and the more constraints, it is fast. It is reasonable fast, but still takes a fair amount of time. You can probably see here that even the burn-in phase, perhaps I should probably try to change something before I'm just going to change the export OMP. Set it to all 4 and try to run it again. See if that helps. Alright, just like before, I'm going to pause the video and then come back when this run has almost concluded. See you in a bit. Alright, so the run has concluded in the source plane optimization. I've opened the best.par file. Remember, this is still source plane optimization. So as you can see, the X center, the Y center are somewhat off, actually a bit. The ellipticity is reasonably close. The angle position is also reasonably close. The core radius in kiloparsecs, it is somewhat off, actually a bit off. The cut radius is not optimized, so it is the same. And the velocity dispersion is also to a reasonable degree fairly close, even though given that I am using source plane optimization. So let's take a look at the it is so that since I chose the magnitude, the reference magnitude to be 17, sorry, this galaxy here with the magnitude of 17 is going to represent the reference numbers. So you can see that the cut radius has been set to has been found to be 414, where the reference is 375, somewhat off, and the velocity dispersion is 297, whereas the cut radius in ArcSec is 93, while the true the cut radius has been set to 60 in kiloparsecs, whereas the cut radius found in Lenstool and source plane optimization is 414, so that is highly offsetted. And also the velocity dispersion was set to 375, whereas what was found was 297, so this is also to a reasonable degree fairly off. Let's just check that I set the correct values. I set 4, this is okay, and 2.8571, this is also okay. So this is most likely because I am dealing with source plane optimization. So let's run the bias results command and see what we got. Well, you can see that our cut radius is somewhat off. You can see here that we have a red number. This red number means that for some reason our cut radius for the galaxies has hit a limit. So one of these numbers, and I'm going to look at the mode, is close to the limit. And let's look at what we got, because we set it to. Now the thing is that we set the cut radius between 110 and 100. And for some reason this is offset. So another little trick that you can use is to go up at the output from Lenstool. You can see here that we have 4.38 here, 4.438. This says that at redshift 0.3, 1 arc seconds is equal to 4.438. And down here I got the cut radius here in arc seconds, so I can use this command here and then set scale equal to this number, and then I get it in what you call it in kiloparsecs. Now you can see the mode is 428, and I have limited at, I'm sorry, I'm just going to run it again like this. You can see it is 96 arc seconds. I have set the cut radius to 100, so I could probably set it to something like 150 and then run it again. And so I could go on until all my numbers are no longer red. When I have done this a couple of times, I will go over to reduce the priors. You can see the values here, to constrain them more at the actual values, and then run the model again, but this time optimizing it in image plane optimization. Now I'm going to do that on a server, and as you will probably notice when I started, it will take a reasonable longer time to converge, even for the burn-in phase. So I'm going to let you see that I started, and then I'm going to show you the result when it is finished. It will most likely be somewhere around tomorrow. So even with a highly reduced number of cluster members, I have only 11. In my max model there were 175. I have 40 constraints from 20 images, somewhat around 20 images. In my max model I only had 10 images. Alright, so let's start it. Now, as you can see, I still have 40 constraints and 8 free parameters, which is good. But as you can probably also see, the optimization quickly slows down in image plane optimization. So I'm going to pause the video for now and then return when the optimization is finished. Alright, so now the model, the cluster model as I've called it up here, has finished, and you can see now that I have actually run the bias results PL script again, and now you can see that I have no red results, meaning that none of the parameter outputs that I get have gotten in the bias.dat file has hit the limit on my priors. But as you can see, some of the parameter values are still highly offset compared with the true values. Alright, one other thing that I wanted to show you. Now, before I showed you a way to calculate where you got this chi total here, the chi-square, and then I used the model file, and then I changed the signal, the position error, and then I ran it again. Now you can also use another file called bestup.par, and then you can change the chi-square. The difference is that the best model, bestup, uses a Gaussian prior value, meaning that these priors are actually trying to stay fairly close to the priors that you give it, because you are here assuming that you have the best model parameters that you can get. So I'm going to run this model. It should go fairly quickly, but nevertheless I'm going to pause the video and then return when it has finished. Alright, now the model has run through and I've calculated the position error. I'm going to copy that number into not the best .par, not the model .par, but the bestup.par. This file will still optimize the model, but it should retain the values, the optimal values that it gave me, and instead just reduce the chi-square. Alright, as you can see here, I have refined it a bit. I got it to 1.07, almost 1. I refined my position error here. You can see 0.068. Now, as you might remember, when we ran this model only as a singular isothermal sphere, we got away with almost 1 in our position error. Here we can go as low as 0.06 and get a reasonable chi-square. Now I'm going to be really extreme. I'm going to let this run all the way up to 20,000 different models. So that's 200,000 inputs in the bias.dat. And then I'm going to talk with you again when the optimization has run. See you in a little bit. So, I would like to show you now the results from the run of the singular isothermal sphere with 200,000 lines in the bias.dat file, or 20,000 different models. So the run has completed, and let's take a look at the bias.dat file. So as you can see here now, the Perl script takes a lot longer time to calculate the results, because before it only had to look through 1,000 or 2,000 lines. Now it has to look through 20,000. Now it has to look through 200,000 lines. But let's compare the results. Again, you can see we have the best result here for the x and the y. As you can see here, minus 0.0286 with an error of plus 0.0558 minus and minus 0.0621 is as close as it can get to 0.0. And likewise you can see with the y position here, the center of the y position, 0.0715 with an error of plus, it's a little higher, the error here, but again it is fairly close to 0.0. The ellipticity, as you can see here, 0.396, and I chose 383, but again the error is plus 0.053 and 0.045. So again, it is reasonably close. Position angle 125.5, and I chose 123.89. And again, with the error bars, you can see it is as close as it can get. And finally, the velocity dispersion 421.7. I chose 422.9. So again, reasonably close as you can see. Next, I'll look at the results from the cluster simulation that I did. Okay. So I finally managed to get the last model we looked at running, and now able to show you the results. Alright, so as you can see, I had to fiddle a bit around with it. As you can see here, the degree of freedom is still, the degrees of freedom is still 32, but our chi-square got to 30, so we can just simply calculate that 32 divided by 30.61118 is almost 1. So it's actually fairly okay. And if you look at the best opt file, you can see that I got the position error down to 0.069, 0.07, which is also pretty okay. Usually when dealing with true systems, not mock systems like this, you'll get a much higher position error. So let's take a look at the results. The original results that I gave the model was 0.15. Our best results is 0.099, 0.1 sort of, and the Y center was 0.20, and we got 0.23, which is pretty close. Our ellipticity, where we created these images from, these images here, was 0.30, and we got 0.30. The angle position was 120, we got 119.8, which is almost 120. The core radius, we set it to 90 in kiloparsecs, remember that? This is in arcseconds, so when we convert it, the core radius the model gave us was 92, and of course the cut radius was fixed. Our velocity dispersion for the cluster halo was 1250. We got 1249.4. This is pretty damn close, I'll say. Let's take a look at the cluster members. As you can see, most of these parameter values here are fixed. This is because this is the reference galaxy. We can just look at it because it will give us the correct results. So as you can see here, we gave it a cut radius of 60 kiloparsecs, whereas the model gave us 76. So it's almost 77. It is a bit off, not much, but a bit. But in respect, when we look at the velocity dispersion, the sigma value, we gave it 375, and it gave us 375 smack on. So one explanation for this is that, like I've said in a previous video with the results from my master thesis presentation, you actually need multiple images around galaxies in order to constrain these values here to a significant degree. Now, if we look at over here, I have the results with error bars. Do mind you that I increased the number of samplings to 5,000, so we got 50,000 lines instead of the usual 10,000 lines. But as you can see here, if we look at the X position of the halo, that was a little off. It was 0.0996, but we got plus 0.07. So let's try to put that in. 0.0996 plus 0.07. Where was it? 716. We got 0.17, and the correct number was 0.15. So we're actually within 99% certainty with the correct value. Remember, again, this is the best value we got here. And also, what was also a little bit off, it was this number here. The best value that we got was 17 point. Let's put that in. 17 point. Remember, this is in arc seconds, right? So 17.2376, and then we need to take minus 1.1846. It gave us 16.053, and I don't have the correct number in arc seconds, so we need to convert it. And I think I have the correct method in here somewhere. That was. Let's see. I'm gonna take a little look, and then I come back to you. Alright, so now I'm ready. Let's take the bias results. Then we can put in another parameter where we put in the scale. This number here means that 1 arc second, which is the values that we got here for most of them, is consistent or is the same as 4.454 kiloparsecs in that particular redshift and that cosmology. So let's try to run it. Now you can see that the position angle changes, and that means that if we compare these values here, they will be highly off, 119 and 209. So we can't really, this is not something we should look at. But we can see here that we get the cut radius. Let's take a look again. We got 76, yes. And then we can subtract 5. So our quick eyes will tell us that this is not enough. 76 plus 7763 minus where was it? 5.2760. It will give us 71. It is still 11 off. But again, please remind yourself that we don't have multiple images around all the cluster members, so that is probably most likely why this value here is somewhat offset. Alright. Another thing I would like to remind you of is that this is exactly what I meant by having a system where the lensing equation, when we invert it, this is what we have done here, we have inverted the lens equation, is non-linear. if we had a linear system, if this were a linear equation, then giving Lenstool some masses in here, I can open the, I think I have the, here they are. If I give Lenstool these masses here, put in some sources, and then get these images here, giving some parameter values, again remind you that I'm talking about a linear system. If I then invert this system, so I take these images and then try some parameter values and try to compare to the best fitting with the images, then I would get in a linear system the exact same numbers. Completely exactly the same numbers. This is what is meant by a linear system. So for example, if you take let's say if you take your distance you have traveled and divide it by let's take a simple example, I can calculate it here. So let's say that we have, this is a linear system. You all know that if we take the meter per second, then this is a velocity, right? So let's say we have traveled 1,000 meters and it took 250 seconds. Then we know we have traveled with 4 meters per second. So if we invert the system, so let's say if we travel with 4 meters per second for 250 seconds, we will travel 1,000 meters. So this is an example of a linear system, a linear equation. You can see it might not be that obvious to you here, but I have actually inverted the system. First I took up here, I took the meters that I traveled and divided it by the time I traveled, and then I got a velocity in meters per second. Then I inverted this equation here. So instead I said, well, I'm traveling with 4 meters per second and I travel for 250 seconds. How many meters do I travel? If this were a non-linear system, I might as well have gotten 560 meters. Of course, these calculations here in Lenstool are much more complicated, but the idea is still the same. So given that this is a non-linear system, and of course this is a relatively simple system, I could have put in I put in 11 cluster members, right? And usually you use somewhere between 40 and almost 200 cluster members. We also in the new data from the MUSE telescope on the new MUSE instrument on VLT, we got over 200 multiple images for the cluster I've analyzed in my master thesis. I hope that you have gotten a little insight into how Lenstool actually works. Of course, I have used mock catalogs here, but the principal idea in optimizing a system in Lenstool is the same. I'll just quickly recap. You get some multiple images. Then of course in a true system you would take spectroscopy of all these images that you can see, or all of them that you can get spectroscopy of, because this is a mock catalog without colors. You cannot really distinguish the images from each other. You will be able to do that in a true system, in a real system. Because you can also see where the galaxies are positioned. It is likely that we have a galaxy here. Let's try to blink it. That was. Yes, you can see we have a galaxy here that influenced these images here, and also the same down here. Right. So galaxies, multiple galaxies, or the cluster members will only usually perturb the images, but the central bright galaxy in here might possibly create multiple images as well. But the idea is, to recap, that you set up your parameter file with your potentials that you want to optimize for. This is the priors that you put in, so this is sort of the way you restrict your what do you call it, exploration of the parameter space. And down here you could have you set if you have cluster members, that instead you could also put all the cluster members in like a potential like this. But let's say you have 100 cluster members and you have 6 free parameters for all of them. Let's say that you exclude the centers, so you only have 4. Then you would get 400 free parameters just for the cluster members alone. So that's not doable. Instead, you include them in this potential file here, where you include the position. If you want to include the shape of the galaxy, it's here. So you get an ellipticity from an A and a B, the minor and major axis, or major and minor axes, and then a position angle here. Then you include the sorry. Then you include the magnitude here, and the luminosity of flux here is not used. Remember that whether you use AB or any other kind of magnitude system is practically irrelevant. The only important thing is that the magnitude that you put in here, system that you use here, and the magnitude that you give it here is in the same system. So you can say if you use the brightest galaxy as your reference galaxy, you'll almost always get the same magnitude here. Then again, you set some priors. In these priors, you can sort of use the priors that you would expect usual galaxies to have. So I would say a cut radius between 10 and 150 arcseconds is probably okay. And again, a velocity dispersion between 10 and 600 is also okay for galaxies. Usually you could actually expect this to be between 100 and 60, but here you include the possibility of very, very faint small galaxies. Then you put in some other parameter values here in Lenstool that I have already described. You set the inversion parameters, how much you would like to, how much detail you want to get from the burn-in phase, you set here. Somewhere between 0.1 and 0.05 is usually consistent for a very detailed look. And then you set the how many sampling you want to run in order to sample your parameter space. Again, it's very simple. If you set a low number of samplings, your optimization is relatively fast, but you might exclude the best parameter value set. If you set a higher number of samplings, for example the 20,000 I selected, then you would most likely hit the best sampling point, but it would take a much longer time to sample, especially if you have a large cluster. And then you set in here in the image file where you put in your images, mult WCS you can exclude because this is deprecated, but in the former optimization here, you select with 0, you're running source plane optimization. If you set it to -1, you'll run image plane optimization. You have to include this value, this parameter option here, even though you are not optimizing any multiple images. For some reason, Lenstool needs this parameter value here in order to run. And finally, the position error, you select something that seems reasonable. If you're using Hubble space imaging, you can set it to the pixel resolution. So usually that is either 0.065 or 0.03, but most probably on a real system you would end up with a position error somewhere between 0.3 and 1.3, something like that. Alright, that should be all. Of course, if you have any questions, you're very welcome to put some comments on this video. I hope you have enjoyed it, and I hope that you have gained insight into the basics of how Lenstool works. Thank you for watching.